Hello and welcome to a new episode of TarGZ. Today we talk about text retrieval and how to use inverted indexes with sparse vector representations of queries and documents. The topic is quite technical, so I will let Franco Maria Nardini, Research Director at ISTI CNR, explain it while we discuss his paper titled Efficient Inverted Indexes for Approximate Retrieval over Learned Sparse Representations. Hello Franco and welcome.
Hello, Luca. Thanks for the invitation.
Yeah, it's a pleasure to have you here. And would you like to introduce yourself?
My name is Franco Nardini. I'm a research director of the ISTI CNR, which is an acronym for Istituto di Scienze e Tecnologie dell'Informazione, National Research Council of Italy. I'm based in Pisa. And starting from my PhD, my research interest mainly focus on information retrieval, and the last, let's say, decade, it also involves AI applied to retrieval, efficient AI, and all other things that revolve around such kind of, let's say, keywords.
Cool. And so, talking about your research, let's jump into the paper. Would you like to give us some context?
So the paper is a paper we published in CIGIAR 2024. In this paper, as the title suggests, we tackle approximate retrieval, and indeed we do it using an efficient solution involving inverted indexes. What we use here is learned sparse representations. And to understand what are learned sparse representation, we need to come back to 2018. We all know 2018 BERT, large language model, came on the scene, and indeed BERT is, let's say, shows that large language model had at that time the potential to easily impact both natural language processing and information retrieval also. Specifically, from 2018, one line of research focus on representations. What does it mean, representations? Instead of using this big, let's say, model in production, we use the model offline to build representations of objects. What is a representation? A representation is basically one vector, okay? So we have this representation, and the representation is very interesting because many papers shows that those large language models are able to transfer the semantic information in the original domain into the latent space of the representation. So computing in information retrieval, computing similarity for a query between queries and document becomes computing something in the latent space, which is L2, inner product, or cosine. Okay? That's the interesting part. Representation coming from large language model allows to transfer an idea, let's say, of similarity search into mathematical operation in the latent space. I told you in this paper we focus on learned sparse representation. Why sparse? Because from that time up to today, the literature focuses on basically three kinds of representation. Sparse is the last one. The first two are dense, so the representation is a dense vector of real numbers. Multi-vector, what does it mean, multiverso? Instead of encoding the query or the document into a single vector, we go down in the granularity, so we encode each term into a vector. You may imagine a lot of vectors in that kind of, let's say, in that family of encoders. The last one is sparse, and sparse is very interesting because now the target is a sparse vector where dimensions are grounded in the vocabulary. What does it mean? I have a query, I have a document, an encoder in the middle. My encoder encodes queries and documents into a sparse vector of terms. So the question here is now, why do you need to encode something which is text in something which is text again? Because there is this interesting property of sparse encoder, you can learn to expand, no? So you have a query which is generally short, and the encoder expand the query into a bigger one that include terms that are semantically related with the original query. So to fight, naturally, vocabulary mismatch, which is a very well-known problem in information retrieval. Queries and documents go through the encoder. You encode into a sparse vector, which is now expanded. This is super interesting. Indeed, literature shows that by doing that in many different flavors, you can, let's say, learn encoders are very powerful in terms of effectiveness. What is the effectiveness? Basically, the retrieval quality measured with some, let's say, metric from NDCG to MRR, depending from the scenario.
Sorry, a question. When you say expand the query, you mean that like I issue a query and then you can, let's say, retrieve results without really looking at the exact word that I'm saying. So you look at what I mean with my query, and so you can find basically all the answer to semantically similar questions.
Let me try to be very, very clear with an example for our friends at home. The example is the following. What shoes do most NBA players wear? Okay, super, let's say, basic query that involves indeed players, NBA shoes. Okay, if you go through Splade V3 encoder, which is a state-of-the-art encoder, sparse encoder learned on text, the representation you have is MBA with very high score, because indeed that word is very important, shoes, which is very important, players, which is also very important. Those are the three keywords I expect to be there.
Yeah.
But the encoder also had basketball, okay, which is also very semantically related with the original query, but not in the original query. And basketball is something for that encoder much more important than players, for example, which is sound. I expect that, because it is somehow a synonym of MBA. Indeed, it's the, let's say, it's the sport where MBA is related to, no? That's the concept of expansion. And the process of expansion involves both queries and documents. So you basically have a representation which is still sparse as the original text, but indeed, let's say, include much more terms just to fight the vocabulary mismatch. Now, there is one problem. Why sparse? Because indeed, in information retrieval, people were used to sparse indexing techniques. What are sparse indexing techniques? Basically, applying inverted indexes on top of text. Okay, a lot of, let's say, research in the last 50 and more years for that. Super efficient solutions that allows to fetch, let's say, important results in a blink of an eye. But things changed from 2018 on. Why? Because indeed, while original textual collections were, let's say, characterized mostly by two properties. First, in web search, queries were short. What does it mean? A query were 2, 3, 4 terms at most. First point. Second point, text terms into document collections was distributed following a Z flow. The two things with neural encoders does not hold anymore, okay? Because queries are longer, also because we have an expansion. Documents does not follow anymore the zip flow. And inverted indexes were evilly designed to exploit such kind of properties. So what were working very well nowadays doesn't work anymore as before.
Can you just quickly explain what is an inverted index?
Inverted index is a data structure that indeed allow to be, let's say, allow to search over a sparse representation as the text is, just because you basically have a structure that links terms to all the documents that contains that specific term. Okay? When you have a query, you look at the so-called posting list. So all the document lists that are indeed linked to that specific term and just focus on top of that, disregarding everything else. Okay? That's the main idea behind the standard inverted index. Then there is a ton of literature on how to optimize it. So a lot of tricks to, let's say, somehow have that kind of traversal super very efficient. And that was working like a shot. With neural representation, that kind of machinery doesn't work as before. So we need to work on finding new ways to have efficient inverted index, efficient retrieval with learned sparse representation. That's what we did here in this paper. We introduced Seismic. Seismic is an acronym that indeed leads to this data structure, which is composed of two main ingredients: the inverted index I was telling you before, and one forward index. I will go through it in a while. The inverted index, I told it before, links terms to documents, okay? The forward index, you can think to it as a lookup table. You go with the document ID, the forward index gives you the full representation, the full vector of that document, okay? So all the seismic idea grounds on one property we discover on top of the most important encoders, sparse encoders in literature. We call it concentration of importance. What does it mean? You have a sparse vector, which is the result of applying an encoder on queries and documents. Only few components of that vectors are very important to determine the final inner product between a query and a document. You don't need to have everything. You just can keep something. And this is very important because according to this property, if you want some numbers, you can somehow estimate the dot product between 90% of the actual dot product of a query document pair just by looking at 15% of the terms of the representation, the most important ones. The most important 15% of queries and document vector you put together and you have almost 90% of the overall. What you can do is now try to redesign the overall data structure with this property in mind.
And that's what you did, right?
And that's exactly what we did. Because what we did is to use the inverted index for filtering and looking at, let's say, very promising documents. And then we use the forward index on top of this set returned by the inverted index to understand if we were right or not with our estimation of the dot product. The inverted filters the forwards allows to compute the exact dot product between queries and documents. Now, the inverted index is a filter, and what we need to do is in order to be very efficient with the retrieval, we need to work on top of that to exploit the full, let's say, potential of the property we discover. What we did, without going into too much detail, is to, let's say, build on top of the inverted index, on top of the inverted index, several techniques, which are several families of techniques. One is static pruning, the other one is dynamic pruning. First, super simple and intuitive. Instead of keeping all the documents for every term, why do I need to keep documents that have low importance for that specific term? No, it's not indeed interesting because I know that that term would not be useful in the computation of the inner product with that specific document. So static pruning says remove low importance documents from the posting list for the specific term, and that's it. Dynamic pruning, what does it mean? instead of considering all the components of the query, just focus on the top 15% of the components of the query and use only that against the inverted index. Then there is also an interesting part. The interesting part, which is, I would say, the most novel, what if, from an intuition point of view, what if inside one single posting list, we put together documents that are similar and we group them into one single block, then we somehow represent that block with what we call summary. It's basically one vector that is an approximation of the best possible inner product I have visiting the documents inside the block.
Okay.
So building the summary, introducing the concept of summary allows me, instead of computing all dot products with all the documents in the block, just compute the upper bound I have with the summary and asking, is this upper bound interesting for me or not? If no, I can just keep the whole block. So summaries introduced by us in this paper are an upper bound approximation of the possible inner product achieved into the block. I go scoring my query with the summary. If the upper bound is not, let's say, interesting, let's skip and we go to the other block, to the next block. Now, considering that we block according to hyperparameter tuning, but indeed every block has more than 10 documents, we can easily say that we compute one in case we skip or one more in case we then visit the block. But if we skip a lot. Okay, Luca, are you following me?
Yeah, of course. I mean, you're basically reducing a lot the surface where you do the search by grouping similar documents together and understanding if the query is relevant for that group of documents.
Now, using this kind of machinery, so going through summaries and, if interesting, also visiting blocks, we are able to reduce a lot the number of dot product computed for every query arrived to my system. Then I save the interesting documents from this process, which is the query processing algorithm we introduce in the paper. And for the interesting part, now I also need the full inner product, because this is an approximated for the pruning stuff process. So for the ones that I consider interesting, I go on the forward index and I compute the full inner product of the query document page to build the final list of results. This is seismic, okay? It's a two-level inverted index plus a forward index. For every query, we traverse the inverted index using skipping over blocks to identify an approximate list of documents that I consider relevant, and then with the forward index, I compute the full inner product of the computation. That's indeed what we introduced. Now, the point we were asking at the time is, okay, but given all of this, what is the performance with respect to the state of the art?
Yeah, exactly. That's what I was going to ask. What result did you get out of this?
At that time, we were following with a lot of, let's say, curiosity, the results of the Big NN 2023 challenge at NeoRIPS, introduced a Sparse challenge. What is the Sparse challenge? Fast retrieval over sparse representations. And we were very interested because the two winning solutions of the challenge were two graph-based solutions. So indeed, solutions that use HNSW, hierarchical navigable small word algorithm, very well known in KNN search, which works with a super different approach, a graph-based search. But we are, let's say, efficiency guys in IR from many years, so we said, how is this possible? How is it possible that inverted indexes are not in the scene for the winning solutions. So that were the two natural competitors of our new strategy, which we know were state of the art at that time. And that's why we started a comprehensive, let's say, experimentation over 4 different encoders, state of the art encoders at that time. Now, no more, but because there are new encoders, but at that time, the 4 encoders we used were state of the art. And indeed, what we discover is that if you introduce a, let's say, double index machinery like ours, you are able to come back to inverted indexes that are state of the art again on top of learned sparse representations, because we show that, for example, if you consider Splayed popular encoder over Evans Markov popular collection, we are able to achieve from 2.6 up to 3.5 times faster retrieval than the winner of the Big NN challenge.
I would say a very good improvement.
Yes, indeed. With this machinery, we are basically able to achieve 98% of recall on top of MS Markov V1 in almost 500 microseconds, which is super interesting result. While same scenario, PyNN requires more or less 2 milliseconds. So we are indeed 3.5, 4 times faster than the state of the art at that time. So in terms of speed, we were happy because we are now state of the art. But what about the memory? There is also the memory means the space required by the index, no? And what we did is indeed we test also in terms of space required to store indexes, and we show that the space required is more or less same order than PyNN, which is the best from Big NN 2023 challenge. Specifically, PyNN requires over MS Markov V1 more or less 5.5 gigabytes, while we require 6.5, so 1 giga more. But the interesting story also here is that in terms of time for building the index, Seismic, our method, requires 5 minutes, while PyNN requires 137 minutes on the same collection. So we are super fast in building the index, which is expected because an inverted index is way faster in building time than a super complex graph structure like PyNN, with comparable space.
Oh, yeah, sounds super interesting and a very good, let's say, improvement over state of the art. And so my next question is, what were the kind of next steps here? Because yeah, it sounds like a very promising research. So I guess you have several follow-ups on this.
We investigated a lot of ideas, and we are still investigating several, let's say, branch of research starting from this. One is inference free. I told you, queries and documents go through an encoder. Online, so when you use the infrastructure, the query need to be encoded online. What does it mean? The user types the query, you encode the query, and then you do retrieval. So with this infrastructure, now encode time is no more negligible. The question is it possible to remove that cost, that encoding time cost? The answer is yes, introducing inference free, which is a way to pre-compute query encodings without going through the encoder. I won't go into details for this because it's quite, let's say, it's basically learning without context from the beginning so that you can look up directly the weights of every term of the query. That's a super interesting research direction, which is investigated not only by us. Last SIGIR, which is our premier conference, 3-4 contributions were focusing on inference-free encoders, inference-free retrieval architectures. Second point is why do graphs are very, very good in retrieval? We were quite, let's say, surprised of this. Is it possible to define mixed retrieval strategy? What if my inverted index exploits the good part of the graphs, which is global relations, instead of focusing only on a per term basis, which is what this data structure did? We have another paper in another conference, which is CIKM, that shows that if you go through an interplay of the two, you are also able to do even better than Seismic. So you basically reduce the latency, the query latency, without hurting the effectiveness performance, just because you pay a bit more space to store the neighborhood of every document. If I touch one document, I also explore the neighborhood, which is given by a graph structure. If you do like that, you are also able to reduce time just because you have more information on the neighborhood every document shares. That's a second research direction. Then there is a third to close research direction, which is exploitation over resource-constrained devices. We investigated how to do retrieval over resource-constrained devices in our tests, Raspberries, super limited Raspberry 3B, with 1 gigabyte of RAM. And we show that with this machinery, you can retrieve on top of such kind of architecture, doing 200, 300 queries per second with super limited resources, which is something super interesting to me, because indeed, those are devices that cost $20, $30, $100, and they indeed allows very interesting, even in their, let's say, extreme limited editions, they allow to retrieve up to 200 queries per second, which is, let's say, not for free at all, at least in my view.
And well, Franco, this is super interesting, really. And
Thanks.
thank you very much for coming to this podcast and share this research. And also, next steps sounds very, very, very promising and interesting. So thank you very much.
Thank you again for the invitation. A pleasure to be here with you and all the friends at home.
Thank you very much for listening. If you want to know more about this research, check out the link to the paper in the episode description. If you like the content, please consider giving a 5-star review in the platform you're using for listening to the podcast. And see you at the next episode of TARGZ.